So thank you firstly to Richard for introducing the rationale that sort of underpinned what was the third study of my PhD research, where effectively we assessed the question of whether or not a 6-week duration of sprint interval training combined with blood flow restriction could result in improvements in mitochondrial biogenesis, angiogenesis, and again looking at some of those performance determinants in cycling. So as mentioned, BFR has been shown to be an innovative technique that might enhance the training stimulus across a number of different modalities. But despite all of the research that Richard has discussed, whether that be increases in homeostatic perturbations, increased expression of sensors, or increased mRNA expression or of some of those signal transducers, there's yet to be any research that demonstrates phenotypic changes, so physiological adaptations at the morphological level. And effectively, that is what we were aiming at achieving with this research project. So there are potential mechanisms, which Richard has already alluded to, particularly that from the Mitchell paper, which demonstrated some upstream markers of angiogenesis or increased capillarity at the muscle for Ki67. And as mentioned by Richard, the review from Dave Bishop, which suggested that there was potential for increased intensities of exercise to result in improvements in mitochondrial function as a marker of mitochondrial biogenesis, and greater volumes of exercise are more pertinent to improve mitochondrial content. So effectively, this research study tried to cover those bases. So we aimed at looking at a 6-week period of training to slightly increase the training volume versus what had been done previously in the 4-week studies by Connor Taylor and Emma Mitchell. We also aimed at adding the novel intervention or the novel analysis of high resolution respirometry, where we were seeking to explore whether or not we could find improvements in mitochondrial function as a more holistic view of mitochondrial biogenesis. Now, this intervention had a total of 22 more sprints than the 4-week intervention, addressing that volume complex. And briefly, the schematic of what the study looked like was a pre-testing week, which consisted of a resting muscle biopsy on the Monday, a VO2 max test on the Wednesday, followed by 45 minutes of rest, and then a 20-second maximal sprint. And then on the Friday, a lactate threshold test. And this was repeated at week 8 of the study. And then a 6-week training block, again, with progressive numbers of sprints. So starting with 3 blocks of 4 sprints, then 3 blocks of 5 sprints, 3 blocks of 6, and 3 blocks of 7. So a slightly greater duration of the study. And ideally, in this situation, we were really trying to target inducing some of those physiological adaptations that Richard's already alluded to. So what did we find? Now, firstly, I'd like to talk briefly about the performance findings of this study. So we found across a number of different parameters improvements over time, both in the control group and in the blood flow restriction group. Now, that was true of VO2 max, which we saw an increase of 2.1 versus 3.2%. Also lactate threshold 1, where we saw an increase of 8.3 versus 10%. Lactate threshold 2, which an increase of around 6% in both groups, and that was true across various methods of measuring lactate threshold. We also saw improvements in some of those sprint variables that Richard also mentioned. So peak power output, we saw improvements of around 2.7 versus 7%, 11% versus 7%, and again 9.2 versus 11.7. But effectively across all of these variables, there was no interaction effect. So we were unable to detect differences statistically between the blood flow restriction group and the control group. What's worth potentially mentioning again is that, as you may have seen going through some of these graphs where the bars are representing means and the lines are representing individual responses, some of the participants were potentially surprisingly decreasing in their performances in VO2 max, peak power output, mean power output. And something that we've considered with the design of this study is our main research question was looking at some of those mechanisms and some of the potential phenotypic changes that we might be able to induce. But over the 8-week duration, there is certainly potential that the participants may have been overreaching when they came to do their post-testing week on the Monday, Wednesday, Friday. When you consider the 7-week block, including the pre-testing, I'm sure the SDC group would be very unhappy if we put an athlete through that and then asked them to go and perform any kind of time trial on week 8 following such an intensive amount of training. It's also important to consider we did ask participants to continue their non-interval based habitual training. The idea of this study was that we would replace the interval sessions with blood flow restriction or sprint interval sessions in the control group. So there is potential that that training volume is even greater than just what the schematic represents that we were supervising as well. So that's an important consideration when we look at the performance data. But as mentioned, the novel aspect of this study and the primary outcome variable that we were interested in is some of those more mechanistic and fundamental phenotypic changes that we hope to induce. So firstly, then, mitochondrial biogenesis. Now, mitochondrial biogenesis is more commonly now being looked at as a number of factors. Firstly, mitochondrial biogenesis is content, which Richard has previously discussed, and most routinely is measured as citrate synthase activity. This is shown in review by Larson in 2012 to be a very well and strongly associated marker of mitochondrial content, which is actually assessed by electron transmission microscopy imaging, which is very, very expensive and a very laborious technique. So most commonly in the literature, this is what we would expect to see. Now, interestingly, in this study, we did see an interaction effect between the two groups, where in the blood flow restriction group, there was a slight, although non-significant in the post hoc tests, increase of 12.1% in citrate synthase activity, whereas in the control group, there was a slight decrease of about 4.6% in the mitochondrial content measured by citrate synthase activity. Now, decreases or lack of changes in mitochondrial content following interval training isn't something that is particularly surprising or atypical. As mentioned previously, intensity-driven training more commonly will influence mitochondrial function, and potentially with the cohort that we were talking about, over an 8-week period, as much as we may have asked participants to continue their habitual training, the training sessions, the Wingate sessions, as you may have seen from Richard's video, are very intensive. So there is the potential that participants sort of zone 1, zone 2 training during that period of time may have decreased. And that's an important consideration when you're measuring or intervening in any kind of training intervention. There is inevitably going to be variability that you can't control for. Potentially an interesting finding is that the blood flow restriction group has shown a 12.1% increase, and potentially therefore some of the mitochondrial biogenesis sort of upstream signaling responses that have been shown following acute bouts of blood flow restriction may translate to something in a mitochondrial content context, as alongside what we'll come on to, which is the mitochondrial function aspect of mitochondrial biogenesis. So when we talk about mitochondrial function, effectively, it's a measure of oxygen uptake at the cellular level. So it's our capacity, oxidative capacity of skeletal muscle to utilize oxygen for the resynthesis of ATP. Now, there's a number of different parameters which you can look at when you perform mitochondrial function analysis, and we attempted to look at quite a holistic approach. So I'll introduce some of those parameters briefly now for you. So firstly, we have leak respiration, and this is effectively a measure of mitochondrial dysfunction. So proton loss during the electron transfer, as the body oxidizes or produces ATP. As we move down the electron transfer system, we can have a loss of protons, which would eventually be utilized for the resynthesis of ATP. So effectively, this is a marker of mitochondrial inefficiency. We then have phosphorylation, which is the ability for the mitochondria to resynthesize ATP in the presence of certain substrates or specific substrates. And lastly, we have uncoupled states, which reflect maximal mitochondrial transfer system capacities. So these are basically producing non-physiological states in the respirometer to allow the mitochondria to maximally synthesize ATP. So we're really seeing if there's been any adaptations in the mitochondria itself outside of what necessarily might be physiologically applicable, which is more what we would see in the phosphorylation states. Now, the mitochondrial complexes that we look at are mitochondrial complex 1 through 4. So as I present the graph in the next part of this slide, if anything has CI or CII, those are representing mitochondrial protein complexes. Anything with CIP is representing one of those phosphorylation states, and anything with an E following it is that maximal electron transfer system capacity. So what we found then is some quite interesting increases in both groups across all of the measured parameters of phosphorylation and electron transfer system capacity over time. So in both groups together, we were seeing increases in phosphorylation and electron transfer system capacity. Now, as I mentioned before, the Larson paper that reviewed the association between citrate synthase and mitochondrial content also highlighted particularly complex 2 electron transfer system capacity and complex 4 electron transfer system capacity as 2 key markers well associated with the maximal oxidative capacity of the muscle. So these are ones that I'd just like to draw your attention to particularly. Now, what we found is a significant interaction effect in these 2 variables, where a more significant increase was found following blood flow restriction intervention compared with the control group. And these persisted when we did post hoc t-tests, so we revealed that also significant values for change pre versus post in the blood flow restriction group, but no change pre versus post in the control group. It's also worth mentioning that the t-test did also show some changes in phosphorylation capacity through complex 1 and complex 2, another quite well established marker of oxidative capacity of the muscle, but the interaction effect was specific to these 2 variables I've mentioned. Now, across those physiological states, phosphorylation, and the non-physiological states, the electron transfer system capacity, we saw changes of 9% on average in the control group, taking them together, and 47% in the blood flow restriction group. So a huge difference between the 2 trials. And this data in this state is corrected to wet mass of the muscle tissue. So typically in the in the mitochondrial respiration literature, you also would correct to citrate synthase activity, which is the mitochondrial content parameter, which I presented in the previous slide. So what we can see here again is some significant time effects with increases across particularly the phosphorylation variables and also the uncoupled electron transfer system states in the control condition and the blood flow condition. And these were significant across both the control group and in the blood flow restriction group. However, when controlling for citrate synthase activity, the interaction effect, or the only interaction effect that we were able to reveal, was with the leak respiration. Now, this is this mitochondrial dysfunction that I was mentioning before, and graphically, when you measure leak respiration, it's in the presence of no ADP in our SUIT protocol. So it may seem like a trivial change compared to some of the other large bars seen in the pre versus post. But what is worth bearing in mind is that leak respiration is likely to increase as respiration increases. So this finding can effectively be extrapolated through some of the later processes further down the electron transfer system. And what we saw was a 7% increase in the blood flow restriction group in mitochondrial dysfunction, which was non-significant, and a 71% increase in leak respiration controlled for mitochondrial content in the control condition. Now, when we look to produce manuscripts regarding these findings, it will be an important consideration to reflect the changes in overall phosphorylation and maximal uncoupled electron transfer system capacity relative to the inefficiencies or the leak respiration that we saw in our findings. But what you can see across the phosphorylation again is a 12% increase and a 59% increase in the control compared with the blood flow restriction. So despite the interaction effects not being there from CIP through to CIV, we're seeing approximately 12% in the control group and 59% in the blood flow restriction group. Now, obviously those values of increase are very large. So it's worth considering that this is one factor in the model that Richard presented of the determinants of endurance performance. So this wouldn't necessarily translate into huge performance improvements necessarily, but it is worth bearing in mind that previous research has shown improvements in mitochondrial function following 4 and 5 week sprint interval training interventions of around 25%. So those values aren't particularly or out of this worldly high, as it were. So what you can take from these findings together, I feel, is that in this early sort of preliminary view of these results, certainly there is the potential across mitochondrial content and across mitochondrial function that the blood flow restriction can augment the stimulus and result in phenotypic changes further down the chain that have been displayed earlier on in the well-established acute responses to blood flow restriction that Richard went over in his rationale. So lastly then, the immunohistochemistry and angiogenesis. Now, it's worth bearing in mind, as I said, this was the final study of my PhD. So the novel findings relating to mitochondrial biogenesis over a longer duration may or may not be reflected in capillarity. Those Ki67 values are still yet to be determined whether or not we have actually seen angiogenesis, and that's my current job to answer. So we're in the process of doing so. It is like 100 cross sections per muscle fiber per time point per participant, so it's about 4,000 muscle fibers to do the cross-sectional area of, and I am deep in the mires of analysing that as we speak. So I'm sure it's wet your whistle, Richard. It is coming soon, as it were. But mainly the biogenesis of the mitochondria is something that is very exciting for us to potentially present, and if we can get something alongside this as well, then I'm sure Richard will be a very happy man by the end of it all. Okay, thanks very much for listening.